Good morning, students. In this video, we are going to see about Internet Key Exchange for IP security. A key management portion of IP security involves the determination and distribution of secret keys. A typical requirement is 4 keys for communication between two applications. A transmit and receive pair for both integrity and confidentiality. The IP security architecture document mandates supports for two types of key management. One is manual key management and the second one is automated key management. Let us see what actually the manual key management. A system administrator manually configures each system with its own keys and with the keys of other communication systems. This is practically for small, relatively static environment. An automated key management system enables the on-demand creation of keys for security associations and facilitates the use of key in a large distributed system within evolving configuration. The most automated key management protocol for IP security is referred to as Oakley Key Management or Key Determinant Protocol and Internet Security Association and Key Management Protocol ISAKMP. Let us see what actually Oakley Key Determinant Protocol says. Oakley is a key management protocol based on the Diffie-Helmen algorithm but providing added security. Oakley is a generic in that it does not designate a specific formats. Whereas the Internet Security Association and Key Management Protocol provides a framework for the key management and provides the specific protocol support including formats for negotiation of security attributes. The ISAKMP by itself does not dictate a specific key exchange algorithm. Rather, it consists of a set of messages message types that enables the use of a variety of key exchange algorithm. Oakley is the specific key exchange algorithm mandated for use with the initial version of the Internet Security Association and Key Management Protocol. Actually, in Internet Key Exchange version 2, the term Oakley and ISAKMP are no longer used. There are significant difference from the use of Oakley and ISAKMP in Internet Key Exchange version 1. Nevertheless, the basic functionality is the same. Let us see in depth of key determination protocol. Internet Key Exchange key determination is a refinement of the Diffie-Hellman key exchange algorithm. Recall that Diffie-Hellman involves the following interaction between user A and B. There is a prior agreement on two global parameters between user A and user B as a large prime number q and a primitive root of that prime number q as alpha. Let us see. The user A and B shares a prime number q and integer alpha such that alpha is less than q and is a primitive root of q. Meanwhile, user B also going to select the same thing. Next, user A generates a private key XA such that XA should be less than Q. Similarly, user B also generating a private key such that XB is less than Q. Later, A calculates a public key as YA is equal to the primitive root of Q alpha to the power of XA mod Q with its private key and found its public key as YA. Similarly, B also going to calculate the public key and B found public key YB is equal to the primitive root of Q alpha to the power of B's private key XB mod Q and he found its public key as YB. Then user A shares its public key to the user B. Similarly, user B shares its public key YB to user A and receiver A receives B's public key YB in plain text and user B receives A's public key by A in plain text. Then both user A and user B are going to calculate their shared security. With the help of the formula K is equal to YB to the power of XA mod Q, they are going to calculate the shared key. For user B, they are going to calculate K is equal to YA to the power of XB mod Q. And finally, they are going to calculate their shared key as K is equal to and B K is equal to. And now we are going to see about this. The key which have been found by the user B and the user A both are similar. Such a way, this shared key has been found with the help of Diffie-Hellman key exchange, and they are going to start the session. The same can be explained in a text manner. Large prime, then a primitive root, and both has to choose their private key and how to calculate the public key. With the help of that public key, they have to calculate the shared session key. Finally, the shared key Ka is equal to Kb. Both are similar. So here the attacker, when they want to attack, they needs the X value. This may be resolved or solved by using a discrete algorithm. But before entering into the features, we will see with an example of Diffie-Hellman. User A and B are going to swap two keys, agrees on a prime Q is equal to 353 and alpha is equal to 3. And they select the random key. A chooses 97, B chooses 233. They are going to compute the respective keys. A public key of A is 40 and public key of B is 248. When they are going to calculate or compute the shared session key, A got session key as 160. Same, B also got session key as 160. It's an example which explains the Diffie-Hellman key shared key algorithm. Coming to the two attractive features of Diffie-Hellman algorithm, secret keys are created only when needed. There is no need to store secret keys for a long period of time, exposing them to it may increase to vulnerability. The exchange keys on prior existing infrastructure rather than an agreement on the global parameter.